Hello everyone. Welcome to ML with AP. It's Sunday and I'm back with 5 questions related to data science interviews. Let's start. So the first question for the day is, what is an imbalanced data set and how can one deal with this problem? So friends, we already know, you must be knowing that imbalanced data set cause issues with our model performance or model training. Now let's define what is an imbalanced data set. Imbalanced data set happens when one class of the problem or one class of the label is is in a very high number compared to the other class. So if you see the picture over there, and this typically happens in the classification settings. So if you see the picture over here on the left, if you see the blue dots, the blue circles outnumber the orange squares heavily, right? Probably 10 is to 1, something like that. In case something like this happens, we call it imbalanced data set, where one class of problem occupies 90, 95, 99% of the observations and the other class label is only 1%, 2% or 5%. So in case of histogram, if you see the Y label, right, in the case of histogram, it will look like this. One tower will be very high relatively to the other tower. So this is called imbalanced data set and it happens in the classification settings. Let's see why it's a problem. So let's first try to define that, why it's a problem. So let's take for example that we have a let's say some disease data set, okay, where 95% of the and in that data set 95% of the people is from class 1, 5% is only from class 0. Okay, so it's a binary classification problem, class 1 and class 0. Let's say this is true class, positive class, negative class, whatever you want to call it, but it's highly imbalanced. 95% belongs to class 1, 5% only belongs to class 0. Okay, now the question is that, okay, if we train our model on this, okay, what is going to be the accuracy? Suppose the model which we have trained is a very dumb model, right? It's very dumb in the sense that all the time it will predict only class 1. All the time it will predict only class 1. What will be the accuracy? Suppose if a new observation comes and I have to do the prediction and my model by default 100% of the time just gives the output, okay, this observation, assign it to class 1, assign it to class 1. What will be the accuracy of that particular dumb classifier? Because in the population itself we are getting this 95% 5%, right? Okay, the next observation, by sheer chance the data will be 95% of class 1 and 5% of class 0. What it is going to classify? The accuracy obviously will be 95%, correct? Because the population itself is highly skewed. 95% belongs to class 1, only 5% belongs to class 0. Think of as a scenario like a disease which is very rare. A disease which is very rare. In a population, only out of 1 million people, 5 people out of 1 million, 5 people get that disease, right? If we are if we are taking a sample, an imbalanced sample from the population, and we are training that model, what our model is going to learn? Our model is going to heavily classify everything as what? As no disease, right? Because the data itself is imbalanced in the case of no disease, right? 99 or 99.99% it is classifying as no disease. If a new set comes to the doctor with some symptoms and we have to put our model, that model will obviously classify it wrong most of the time because its accuracy will be very high. In the population itself, the disease percentage is 1 million is to 1, right? And you're taking that sample. So here is the problem with imbalanced data set. In case of rare disease or some rare events, right, if we take the sample from the population, then our accuracy or some parameter of the classification performance will not be accurate. What we have to do? We have to train our model mostly on balanced data sets, right? Okay, so what is a balanced data set? Balanced data set is both the classes are relatively equal to each other. Is, let's say if it's a binary classification, two class problem, then my yes or no or true or false should be like 60-40, 30-70. It should not be like 99 and 1. It should not be divided that. So let's say the data which you have received is like that. What you will do in that case? So there are certain techniques which we can do. Now I will describe 4 techniques. There are many more techniques, but 4 techniques we can define or describe or we can utilize, which will help us with the imbalanced data set. The first technique is undersampling. So if friends, if you see the figure over here, what is the original data set? Original data set, orange is very low. The blue tower is very high. That means blue tower is the majority class. Okay. What the technique is saying, undersampling. That means to present our training data, to make our training data, will only sample a subset, of our original data sets from the blue, and will take all the orange one to make it look equal. Okay, 50-50 or close to 50-50, right? So this technique is called undersampling. The second technique is oversampling. What is oversampling? Suppose again over here my blue tower is very high, the orange tower is very low, right? This is highly imbalanced data set. I will oversample. What I will do? I will keep getting the samples from the orange and keep putting it over there. Orange sample, orange sample, orange sample. I will oversample it. I will take multiple samples out of my original provided sample and try to build a bigger sample over here, which will be comparable in the terms of number of observations with the blue class. So my orange class will be equal in numbers with the blue class or close to that. That technique is called oversampling. Third technique is SMOT. SMOT means synthetic minority oversampling technique. So this is also something like oversampling, but it's little different. Let's see it with an example. So suppose my minority class is this orange squares and the blue circles are the majority class. What will I do? Based on these, I will try to cook up new synthetic samples, right? You see these green squares? I will cook these up. How I will do that? There are various techniques over there. So I'll not exactly here what we are taking in the oversampling, we are taking the exact observation and we are stacking it, right? Here we are not taking the exact observation. We are only synthetically manufacturing these observations which are very close or similar to this original observation, which is orange squares, right? So these green squares lie in the region, same region, and it will have very similar properties as orange squares, right? So this is called SMOT techniques. And with these SMOT techniques, after that, my data set will become balanced. That means the number of observation for orange and the blue class will be comparable, like 60-40, 50-50, something like that. Okay. The fourth and the last technique again is provided is that we can weight. So suppose our data set is highly skewed, right? Like this. Okay, it's imbalanced. What we will do? We can assign in our model that because my data set is 1:10, the weight of the minority class is 10, the weight of the majority class becomes 1. So it will offset, by doing the weighting, it will offset the original distribution, which was skewed, right? So the way you can do it in logistic regression, let's say the logistic regression, every will have some parameter. In sklearn, they usually give you the parameter, right? To do that. Then you can define the class weight. Like my 0 class becomes 1, my positive class is 10, right? So you can give the weight. And it is passing a dict, right? If you see, the way to read this is the first is the class, the 0th and first class, right? So this is like my blue and this is like my orange, right? The class 1. My blue class gets the weight 1, my orange class gets the weight 10. So my minority class gets a higher weightage, right? Which will offset, what it will offset? It will offset the original imbalance in the data set. Again, there is a imbalanced learn Python package, and it's very useful. It has inbuilt techniques. So you want to check out, let's check out imbalance. Just search in Google imbalance learn, and you will get the Python package of that. Okay, so that's about imbalance learn and how we can fix it. Let's move on to the second question now. The second question: what are some ways to make your model more robust to outliers? Now we know that outliers are always a problem, right? If you do a exploratory data analysis, outliers is a problem. If you do our any model, let's be it linear or logistic regression or any model, in case if there is outlier, then it will, most model are sensitive to outliers. There are few models which are exception to that, we'll see, but most models are outlier, are sensitive to outliers. And because of those outliers, what will happen is our model performance will go for a toss. So what we can do to make our model more robust or more immune to outliers? So the first technique is add regularization. Now, I do not want to get into the detail of regularization, but there are two types primarily, or multiple types, but two majority type of regularization, L1 and L2 regularization. What regularization does is it reduces the variance. It reduces the variance. So it dampens that if my model is very complex and chasing the noise, by adding the L1 or L2 regularization, and L1 regularization is nothing but the absolute distance, the L2 is the squared distance, right? So if I add those L1 and L2 regularization term, it will dampen it, it will slow it down, it will smoothen it out. So my model which was chasing the noise and had high variance, the variance will reduce, right? How it will help with the outliers? So my model was chasing the outliers also, right? And if I add the regularization component over there, let me see if there is a picture somewhere. Yeah, if you see, let's say this particular thing is my data, my model is chasing the noise, right? It is fitting. So this is a high variance situation, and which is also called the overfitting situation. If I do regularization, L1 or L2 regularization, let's say I get this particular fit. Okay, what is happening over here? This will have better predictive power. This will be less sensitive to outliers. Suppose there is some outlier over there, right? My curve will still go like this. So regularization will, in that case, help with the outliers. Okay, it will make our model less sensitive to outliers. Try different model. This is the second technique. What does it mean? I was telling you that there are some models which are more sensitive to outliers. There are some models which are less sensitive to outliers. So usually tree-based models like decision tree or random forest, gradient boosting, these will be less sensitive to outliers. So use those models which are less sensitive to outliers. So you do not have to deal with outlier also, because my model itself takes care of it, right? So use those kind of model. The third technique is Vinserize data. What is Vinserization? Vinserization is like, what are outliers? Outliers essentially are the extreme points, right? Which is not following the traditional norm, right? Where majority of the data is stored or located, it is not following that path. It is located somewhere off, right? That is called, so in that particular case, if we have to do a percentile, let's say, or decile or percentile analysis using box plot or any other technique, then you will know that my outlier will always be in the region which is above 90% or below 5%. It will be the extreme observations, right? So Vinserization is a technique. What it says is, don't just blindly remove the outliers. That is one technique, right? Removing the outliers. Don't just remove the outliers. What you do is, instead, you make a rule that anything which is below 5%, below 5 percentile of my data, I will all club them as fifth percentile. Whatever was the value at fifth percentile, I will remove all those outliers and I will fill it with what value? The value which was at the present at the fifth percentile. Similarly, on the top side, let's say I'm doing a 95%. So above 95 percentile, whatever is the data, I'm considering that as an outlier. And I'm editing those values or observations as what value? As my 95 percentile value. So everything in a graphical form, if you see, if after Vinserization, everything will squeeze back to 95%. Anything ever 95th percentile will squeeze back to 95th percentile. Anything beyond 5th percentile will squeeze back to 5th percentile, right? So you are anyway eliminating the outliers, but you are not completely removing it. You are replacing it or imputing it with some relatively similar values. Okay, that is visualization. So that is another trick which we can do. Transform the data. So sometimes what we do is that if there are our outliers present, and before we do or fit our model or do our EDA, we should try to do certain transformation techniques. Log transformation works very well over there. What it will do, log transformation squishes the scale, right? So 1 to 10, 10 to 100, 100 to 1000, right? In a log scale, 1 to 10 is the same distance as 10 to 100 is the same distance as 100 to 1000, right? That's what the log means. So in log scale, if you do the transformation, my skewness or my outlier effect, right? If it has a very high skew towards the right, let's say, it gets more normal, right? So my outliers also becomes part of the data set itself, right? So log transformation also helps with the outlier manipulation. Change the error metric to be more robust. So the way we calculate error for our model, so MSE is very popular error, right? Mean square error, which is the square of the residuals. Change it to mean absolute error. Mean absolute error, the absolute distance between my observed data point and my predicted data point, right? That is our mean absolute error. So what you do is, instead of using MSE as an error metric, you start using MAE. MAE is less sensitive to outliers. Why MSE is? Because MSE is squaring. Understood? So any number, if it is outlier, its effect will also become higher. So let's say our outlier is there, and the distance between observed and the predicted is 10. But if you square this 10 becomes 100, right? Because MSE is squaring. So its effect is becoming more and more prominent. But in case of MAE, mean absolute error, because it is absolute, so 10 will remain 10. 10 will not become 100. Got it? So change the error metric. Now the last way is that it's simple. Like it's very obvious that detect and remove the outliers. So there are various techniques to detect the outliers. You can have the okay, anything within -3 and 3 z-scores or standard deviations, I will ignore it. I can do box plotting. There are various techniques. So whatever technique you do to identify outliers, you remove those outliers from your observation, and then you deal with the data modeling, which will work, right? So these are some of the techniques to make our model robust to outliers, right? I hope you got it. Thank you. Let's move on to the next question. Why is ridge regression called ridge? Okay, so we already know ridge regression, right? What is ridge regression? It's a regularization concept, right? So we were talking about a few minutes back, we were talking about L1 and L2. Our ridge regression is L2 regularization, right? And essentially it's a linear regression, and what we'll do, we'll add a penalty term, a squared penalty term, as a part of regularization effort. Okay, so let's first try to understand what is ridge regression, and what is regularization first. So regularization always comes from the bias variance trade-off, right? As I was saying a few minutes back. So if you increase the bias, the variance decreases. If you decrease the bias increases. So there will always be a trade-off. Okay, I have made a separate video on bias variance trade-off. Please take a look at that also. How regularization helps? Regularization helps by reducing the overfitting and increasing the bias. Again, take this example. Here, few data sets were there. My initial model was this, right? It was going through all the points. It was changing the noise also. And it was very complex model. What do you think? Its variance is low or high? The variance is very high. Variance is high, that means bias will be low. Okay. And it is a classic case of overfitting. So it will work well with the training set, but a new observation comes, a test set, it will not perform that well. That's called regularization. So it will not regularize well with the newer data sets. What we'll do, will employ some regularization technique over here. In this particular case, L2 regularization, which is ridge regression. After that, it will smoothen it out, right? It will smoothen. What we are doing, we are reducing the variance from this picture to this picture. We are reducing the variance. But what we are gaining? We are gaining the regularization. We are gaining the predictive power for the new data set. For the older set, it may not predict very well, because see, there is a residual. There is a gap between the red line and the blue line. Here it was nicely touching all the blue dots, right? Here it is not touching the blue dots. So I'm reducing some variance. For my training data set, my whatever performance metric will be there, MSC will not be very high. Okay, actually MSC will be high, right? Because there is a residual. MSC will not be close to 0. But what I will gain for my future predictions, it will better fit. My future prediction will be better. That is the concept of bias variance trade-off. What is overfitting, underfitting, what is a good fit. And in this particular case, we are dealing with regularization. So this is a cost function, right? Again, if you see any standard literature or my videos also for linear regression, you can see this cost function. This particular function is the MSC, right? So this cost is nothing but the difference between them and the squared. And what I'm adding over here, I'm adding for my theta j. These are the parameters. These are the parameters, theta j, right? Parameters of the equation. So in case of two-dimensional, this can be considered as a slope, but in multi-dimensional, this will be the theta parameters. So I'm doing a squaring of that. This is called L2 regularization, and this lambda is a constant term. It is like a learning rate. It is a hyperparameter which we need to set, right? Typically 0.1 or 0.01 or something like that. So this is the penalty which I'm adding, right? This is the penalty which I'm adding to regularize. Now, how this is helping? Suppose my initial model was this, right? Initial model was this. When I add this particular penalty, right, what it will do is its net effect will be that it should not have these theta j. So there will be theta over here also in the cost function. What it will do is it will lower down because of any higher theta, it will stop making the theta grow to a very large number, because this number is a less than 1 number, right? And this is squared. So whenever my any particular theta j is becoming very, very big, what it will do? It will try to control it and bring it down. And when I bring my slope down, that means I'm regularizing my fit. Okay, I'm regularizing my fit. Okay. Now the next question would be that why it is called ridge. Why it is called ridge? So this is the difference. This is the two graph which you can see. In case of least square, what is least square? Least square is only this term without regularization terms, right? If I plot only least square, then if my two features are related to each other means multicollinearity. If the two feature has multicollinearity, what will happen? In that particular case, this particular case is my MSC, right? So that's why it is convex function. But otherwise, you can see it in the opposite of that. If my objective function would be also opposite of that, right? So if there are two features which are related to each other, which has higher degree of correlation, multicollinearity, in that particular case, my theta will become very unstable. And by unstable, I mean suddenly it will spike. When it spikes, it looks like a hill, like a ridge. Okay, that's why it is called ridge regression. Why? Because if I employ my theta, this particular penalty term for ridge regression, what it will do? It will make this sharp growth, hill-like growth, into a more smooth feature, right? In a more smooth feature, and this smoothness is like from hill it has become plateau. That's why it is called ridge regression, right? So the ridge, and the why it is not showing up hill and upside down, because this is the cost function or the MSC or the loss over here, right? So loss will be always upside down, right? I have to minimize my loss. That's why it is coming at like this. Otherwise, if you see your objective function, it would have been like a hill. This thing would be like a hill. This thing would be like a more smooth plateau, and that's why it's called a ridge regression. So, friends, I hope you understood that why ridge regression, what is ridge regression, L2 penalty, L2 regression, and why it is called ridge regression, right? Okay. Let's move on to other question. State the difference between causality and correlation. This is one of my favorite points, and everybody should understand this point, right? Because this is so fundamental. It has nothing to do with data science or machine learning. It has to do, but in general, it's a general idea also, and sometimes we always get confused. What is correlation? Correlation is nothing but if I have two data series, if I have two variables, right, and they both are going in the same direction or opposite direction or not related to each other, but incidentally it is happening that if one is increasing, the other is also increasing at the same time. If one is decreasing, other is also decreasing at the same time. Let's say that will be positive correlation. Is one increasing, other is also increasing, positive correlation. If one is increasing, other is decreasing, it is a negative correlation. But correlation means only means that, okay, these two variables, right, are moving in same or different direction at the same time, and how good their strength is, how closely they are linked. That is correlation. What is causation? Causation, on the other hand, is more fundamental. It is about the cause and the effect. Like cause and effect. If I didn't study, I will fail, right? This not studying is the cause. Failing is the effect, right? So causation will always mean to cause and effect. Not studying, cause. Failing, and what is failing? Failing is your effect, right? Now, if my two variables are not studying and failing, then they will be highly correlated also. In this particular case, this correlation between not studying and failing is coming because of causation. But that may not always be the case. Sometimes two variables are correlated with each other for no obvious reason. There is no causation involved. There is no cause and effect involved over there. Let's see with an example. Okay. Okay, here, this one. Okay, so this is the figure which I have taken from the internet. So this figure is, if you see over here, the rate of murder in the US. And on the right side, if you see, the Internet Explorer market share. So Chrome started coming and Chrome started gathering the market share. So the Internet Explorer market share started coming down. And this is the rate of murder in US. Now, if you see the correlation, then the rate of murder is coming down year on year, right? The rate of murder is coming down year on year. The Internet Explorer market share is also coming down in the similar fashion. Okay, so if I have to correlate my murder in US with Internet Explorer, it will be correlated very highly, very close to 1. The correlation will be very close to 1. That means it has a strong linking, right? One is coming down, the other is coming down, and coming down with a similar impact, right? So it is highly correlated, and correlation would be close to 1. Now, does it mean that US was experiencing more murder because Internet Explorer market share was high? Does it mean that? Does it mean that if there are less murder in US, it's because Google Chrome has come and the Internet Explorer market share has come down? No, it is just two variables which are correlated by chance. There is no causation involved. So that is the difference between causation and correlation. Here there is no causation. It's only pure and pure correlation. But in case of not studying and failing, there is correlation also and there is causation also, because one is the cause, other is the effect, right? If you go and search on internet, you will get similar figures, multiple things which are very, very distinct. There is no relation between them, but they are somehow correlated with each other, right? I'm just giving you one example, right, over here, the murder in US and the Internet Explorer market. Obviously there is no correlation. Maybe the murder in US has come down because the government has more funding to do with the law and order situation, right? The police forces have become better, or there could be, or the economic well-being of the citizens have gone high, and that's why the crime rates have gone down. Whatever the reason for Internet Explorer market share going down is the new age browser, right? Chrome and other browsers, right? Okay. There is the other one, the family circus. Okay, this I have taken. So this is a child who is flying with his mom, and he's saying that I wish they didn't turn on that seatbelt sign so much. Every time they do, it gets bumpy. So he sees that whenever the seatbelt signs are turned up, after some time, the plane is encountering bumps or some turbulence. We call it turbulence. So plane is encountering turbulence whenever the pilot is switching on the, so he's thinking that because pilot is switching, we are encountering turbulence, but actually it's the other way around, right? The pilot is anticipating turbulence ahead, so he's switching on the seat belt sign so that people can go back and sit in their seat and do. What is the cause over here? The cause is lighting. The cause is the turbulence which the pilot is able to foresee in future, right? And he's switching on the light, and then he's experiencing this boy in his all naiveness. He's reversing the cause and effect. It's very similar to, oh, like what was the cause in the exam scenario? The cause was that I didn't study, that's why I failed. So the cause was not studying, right? And the failure was the impact, right? Let's say I failed is the cause. Okay, the failing is the cause and not studying is the impact, right? Because if we look just at the pure data, sometimes we'll not be able to understand that which is cause, which is effect. That's where the domain expertise also comes into picture, to identify that which should be my target variable and which should be my dependent variables, dependent and independent variables, like which should be my x, which should be my y. So friends, I hope you understood that what is correlation and how it is different from causation. Okay, with that being said, let's move on to the next question. The next question and the last question for the day is, what is the difference between a standard scalar and min-max scalar? What you will do if there is a categorical variable? Now, what is standard scalar and min-max scalar? If you know that these are always used to standardize the data, to normalize the data in case the data, in case my model is very sensitive to different scales of the data, right? So normalization is so the first question comes that what is normalization? What is standardization? What is min-max scalar? Standardization is something which is implemented in a scalar and a standard scalar. Min-max scalar is a min-max scalar. Normalization is another term which we keep hearing. Are they same or different? So normalization, let's understand normalization. So first, normalization is a generic term. So it's a generic term to normalize the data. What do you mean? To bring it on the common range, common scale. So let's say one of my feature is between 1 to million, other feature is between 1 to 10 only. Are they on the same scale? No. Some of the models, some of the algorithms perform very poorly if my range of data of one feature versus the other feature is very different. So 1 to million and 1 to 10 is not on the same range. And if I deploy this model as it is with the observations, then the performance will go for a toss, right? So normalization is the generic technique or umbrella nomenclature which says that, what is it, that okay, bring every feature onto a common range. That is what normalization is. Underneath normalization, there are two techniques: standardization and min-max scaling, right? So these are the two techniques under normalization. What is standardization? So standardization, if you look at the formula over here, right, this is how I standardize. Mu is my mean, sigma is my standard deviation. What we are doing over here, and this z is my normalized value, right? What I'm doing over here, I'm scaling everything down, right, to a standard normal distribution. That is what standardization. I'm centering my mean to 0. Whenever I do x minus mu, that means I'm centering my mean to 0. Centering mean of what? Mean of any distribution which is given. And when I'm dividing by sigma, that means I'm standardizing my standard deviation to 1. Okay. So with standardization, what we are doing, we are centering mean to 0 and a standard deviation to 1. Which other distribution? The standard Gaussian distribution or normal distribution has mean as 0 and a standard deviation as 1, right? That's what we are doing with standardization. In standardization, the what will be the range of values after we, let's say, standardize a feature? What will be the range of value? The range of value can still be higher, but most of the values, right, will lie between maybe 3 standard deviation on the left to 3 standard deviation on the right. 99% of the values, right, if you know the empirical formula, 99% of the values, or 99.5%, I think, will lie between 3 standard deviation on the left to 3 standard deviation on the right. Okay, what will be the 3 standard deviation on the left? -3. What will be the 3 standard deviation on the right? +3. So between -3 and +3, after I do my standard scalar or standardization, between -3 and +3, my 99.5% data, still there will be some outlier we can go out of this, right? But most of the data I am able to squish it into between -3 and +3. If you see between -1 and +1, it's more than 60% of the data will lie between -1 and +1, right? This is what normal standardization does, right? On the other hand, what is min-max scalar? Let's see the formula of that. So this is the new value, the scaled down value. This is my observation. So what I will do? I will do x minus h min by x max minus h min. What will be the result of this, you think, right? Let's say my x is the maximum value. This particular x is the maximum value. What it will become? X max minus h min, and h max minus h min. Numerator is equal to denominator, it will cancel out, it will become 1, right? Let's say on the other hand, my x is x min. So x min minus x min, what it will become? 0, right? So on the left side, I have 0. On the right side, I have 1. What is this scaling will do? What will be the range of this h scale? It will be between 0 and 1. So this is what my min-max scalar is doing. My min-max scalar is squishing all my data between 0 and 1. Suppose I do that for all the features. Now they will come on the similar scale. Everything is between 0 and 1, right? That is what it is doing, correct? And why it is 0 and 1? Why it is getting squished between 0 and 1? You saw it over here. You just replace the value of x max and x min over here. In case of x max, it will become 1. In case of x min, this whole thing will become 0. So obviously my data is only between min and max, right? So the whole data is squished between 0 and 1, right? This is what min-max scaling does. And both standard scalar and min-max scalar are available in scikit-learn, right? So before you run your model, and if your model is sensitive to, let's say, the range of values of the features, then I always urge you to do a standardization or min-max scaling and then run your model for better performance. There are other ways also which I have listed down over here, but these are the two most useful way, and you employ anyway and you'll get significant bump in the performance, right? Okay, so the last part of the question was that what will you do if you are using a categorical variable? So these are all numerical, right? As you can see, we are calculating a standard deviation, we are calculating mu in case of standard scalar, we are calculating min and max, and we are dividing. If it is a categorical variable, not numerical, what you will do? You can't employ these techniques, right? In that, what you will do is, before you send your model to before you fit your model, you have to make your categorical variable into numerical, and the way to do that is through dummy variables or through doing one-hot encoding. Again, your scikit-learn provides a package for one-hot encoding. One-hot encoding is nothing but taking your categorical variables of multi-category. Let's say you have 3 categories, medium, low, high, and you distribute that into 3 columns, right? Or you extend that with 3 features, and then you employ one-hot encoding. That means always one item is the hot, right? That's a separate discussion altogether, but to answer in short, that categorical variable, you can't employ standard scalar or min-max scalar. You have to utilize one-hot encoding to convert into numerical, and then after that you fit your model. And once you do one-hot encoding, obviously the range is always between 0 and 1, so it will fit well, right? The new feature after one-hot encoding will result in 0 and 1. So it will fit well with your other numerical data if you have done the standardization or normalization or min-max scalar. Okay, with that being said, we have come to the last question. I'll see you all next week. Thank you. Bye.